Hello, everyone. Welcome to today's Buoyant webinar, a deep dive into Conduit's Rust-based data plane. In just a few moments, we'll hear from today's featured speakers, Sean McArthur and Carl Lerche. We're going to take a look at the internals of the new Conduit service mesh to understand why certain components are written in Rust, how Conduit is contributing to developments in the Rust ecosystem, and to learn how you can get involved. But first, before we get started, let's cover a few housekeeping items for today's webinar. My name is George Miranda. I help run community here at Buoyant, and I will be facilitating today's webinar. The Crowdcast interface has a few ways in which you can interact with us. First and foremost, we're going to have a QA portion for today's webinar at the end of our presentation. To ask a question, find the Ask a Question section of the menu bar at the bottom of your screen. When you click Ask a Question, you'll be able to submit questions that we're going to answer throughout the Q&A portion of this webinar. I encourage you to submit questions as you have them throughout the webinar as they come to you so that we can be sure to address all of those at the end. You'll also notice that there's a chat interface for Crowdcast, and when any of us presenters aren't speaking, we'll occasionally be monitoring the webinar in case you want to get a message to us. However, if you have a question and you would like us to answer that, please submit it using the Ask a Question button instead of submitting it via chat so that we can be sure to cover it and that we capture it in the webinar recording today. That's it for housekeeping. With that, let's go ahead and get started with the webinar portion. I'd like to introduce today's speakers, Carl Lerche and Sean McArthur. Carl, can you tell us a little bit about yourself?
Hey, I'm Carl. I've been working on open source Rust projects for quite a number of years now relative to the age of Rust. I'm an engineer at Buoyant, and I work on Conduit.
Cool. Thanks, Carl. And Sean, can you also tell us a little bit about yourself?
Yeah. Hey, I'm Sean. Also an engineer here at Buoyant, and been working in HTTP and Rust for a few years. And I'll be talking about the Rust ecosystem today.
Cool. Thanks, Sean. So today we're going to dive deep into the Rust-based internals of Conduit. But before we get started, we should briefly cover the question of what is Conduit. You're attending a Buoyant webinar, so hopefully you are already a little familiar with the concept of a service mesh. But in case you aren't, a brief description is this. So a service mesh is a dedicated infrastructure layer used to ensure that service-to-service communication can be easily managed, monitored, and controlled, right? And so with traditional monolithic applications, typically you know where service requests are coming from and going to, right? Your web servers talk to your app servers, which talk to your database servers. But when you decompose those monoliths into dozens or hundreds of distributed microservices, it's not always clear where requests are coming from or going to, right? Or even necessarily what the relationships are between all of those. So suddenly, the blind spots that live in our network stack between layer 3 and layer 4 and the session layer, right? Those blind spots that we've lived with for decades, suddenly you start to notice them, right? And suddenly they matter, and suddenly they become a problem. And that problem is magnified when different development teams start to own different parts of your application stack, right? And are responsible for different services that power your applications. And suddenly what happens is the scaling and performance benefits of running microservices give way to a new set of problems, right? And those are problems that are highlighted by lack of visibility and control, specifically at the service communication layer. So that's what a service mesh is built for, right? A service mesh shines a spotlight into those blind spots to help make service communication a first-class citizen, right? And the service mesh focuses on providing constructs for observability, resiliency, security, and management, specifically at that service communication layer. So Buoyant provides two different service mesh solutions. We're most known for LinkerD. We will look at both of these options more in depth in upcoming webinars. But here's what you need to know, right? LinkerD is approximately 2 years old at this point. It's a battle-tested, production-grade, multi-platform service mesh that's very feature-rich, and it focuses on providing a maximum amount of control and configuration at that service communication layer. And so LinkerD is written as this really powerful solution that can scale up to handle tens of thousands of requests per second per host. But while LinkerD is really great at scaling up, LinkerD doesn't scale down very well. And we found that that's a prominent use case when managing microservices and doing microservices the right way. So in December, we introduced Conduit. So Conduit is a new take on the service mesh, and it has a radically different philosophy than LinkerD. Conduit focuses on being small, being very lightweight and performant, and Conduit really focuses on reducing complexity by having very few moving parts and requiring very little configuration on your part. And so to do that, we had to make very specific choices to achieve those goals. And that brings us to today's webinar, right? We're going to look at how Conduit is built, talk about the Rust-based data plane that it uses, why that's necessary, and also look at how that impacts the Rust ecosystem. So with that, I'm going to hand it over to Carl to take it from here and dive into today's presentation.
All right, let's see. There we go. Hopefully you can see my slides now. So as George mentioned, I'm going to talk a bit about Conduit and specifically some of the design decisions that we made to build it. One is we decided to use Rust heavily in it. So LinkerD is the other service mesh that Buoyant offers, and it's been around for a while. It harks from an ancient age, years back, 2016. The world was pretty different. Kubernetes was just getting started. LinkerD itself actually came out of some design decisions made at Twitter well before Kubernetes. So the way you're expected to run LinkerD is you run it, you dedicate some servers to it, you run LinkerD on those servers, and all your services running in your infrastructure talks to LinkerD, and LinkerD does all the service meshy stuff from those dedicated servers. So given that that was the design decision, you can dedicate a lot of resources to LinkerD. It was written in Scala to run the JVM, and the JVM definitely, while very performant, has a pretty heavyweight feeling. Nowadays, Kubernetes, all the rage, got to have your containers. Conduit was an opportunity to start from scratch to reimagine what the service mesh would look like entirely for a Kubernetes world. So when the development of Conduit started, there were no sacred cows. We could reevaluate every single decision. So with Kubernetes, there are many containers, and the way you kind of deploy your containers, they tend to be grouped into pods, where a pod is a set of containers that's guaranteed to run on the same host. And Kubernetes offers what it calls the sidecar model. It's a way of extending your containers by providing another container, because everything's containers all the way down. And so the way the service mesh ends up running with Kubernetes is you deploy it as a sidecar, so a container that runs on the same host as your services. This means that every single host in your cluster ends up getting a service mesh container. So the implication there is that the service mesh has to be lightweight, since the process that is running on every single host in a container, you don't want it to take up a lot of resources because there's many instances of it. So the first strategy was to split up what used to be one process with LinkerD, to kind of split it up into two different components, the control plane and the data plane. The data plane proxy is basically the proxy component. So this is where your services on like in their containers talks to essentially the local host to the data plane, and that handles all the logic around routing and retries and everything that you'd expect it to do. But anything that doesn't have to run on the process is split out into what is called the control plane, which is kind of like the brain of the service mesh. That's its own service, and it runs in its own containers, but separately from the data plane component. So one kind of thing is like the control plane, it's going to be a lot lower touch, I guess. Like there's a lot lower request throughput to it. It has to do less work. It has to do a lot of logic, but a lot less frequency. So just for context, the control plane was written in Go. It's a pretty, standard decision, especially in the cloud native world. A lot of these services are written in Go. But the data plane, on the other hand, has very high performance requirements. It's going to be touching, basically, it's going to inject itself in all communications between your various services. So every single byte that gets sent or received goes through the data plane. Besides just high performance, another very critical aspect is predictable performance. So very low latency variance. So it'd be great. I mean, like what you don't want is like very, very fast 99.9% response latency, but then that 1.1% is just ginormous. That's just not ideal for a proxy component. And also security was a very high priority, given that all your data ends up running through the data plane. So when starting to write a new project, as all good engineers, the first thing to do is bike shed the name. And I promise you, there was a lot of bike shedding. We went through tons of internal code names, but that's not what I'm talking about. The second most important thing to do is bike shed the language you choose. And there were lots of ideas thrown around, but roughly speaking, there are two rough categories of languages you can choose from to write a project like Conduit. There's languages that come with a runtime and without a runtime. So by runtime, I mean like a JIT. I guess by runtime, I mean any sort of kind of logic that's built into the process to run your code. So a JIT, Java, the JVM has a JIT. That general strategy is you ship your bytecode. It's not compiled to the end targets, and the JIT does that on the fly. So as the program runs, it analyzes the bytecode and figures out how to compile it efficiently for the runtime characteristics. So some theory, some argue that ends up with more efficient code, because it's when you compile, you're able to see how the code runs in production. That's a theoretical kind of take. In practice, I don't think that works out, in part because, one, you have to warm up the JIT. There's a long warm up. Two, you end up having to hit you can easily hit slow paths, like paths that the JIT has not optimized and will not end up not optimizing. So it ends up being difficult in practice to use a JIT in the context of like a proxy. Garbage collectors, also both Go and Java come with garbage collectors, and this all data ends up getting allocated to the heap. You end up, like when you're programming, you end up using references. You don't have to worry about any memory management. Everything is dealt by the garbage collector. So eventually, the garbage collector has to stop the world. That introduces latency, non-predictability, and it cleans up your heap for you. So, I mean, and there are also lots of other kind of runtime components, like bounds checking or scheduling. Like Go adds a scheduler and stack growth to get around to kind of introduce its green threading model. So because the Go model is to liberally create green threads, it can't just run native operating system threads. It has to implement its own threading model, and one way it allows you to create so many threads is it allocates fewer resources to each thread. So for example, when you create a Go routine, if you're familiar with that, that does not allocate a large stack. That allocates a really tiny stack. And as the Go routine executes, sometimes it never reaches the stack limits, but sometimes it might reach the end of the stack. Actually, pretty commonly, it will reach the end of the stack. And then at that point, Go has to grow the stack. It does this by allocating a brand new stack and copies the smaller one to the bigger one. So in a lot of Go programs, this really doesn't matter. Like when not extremely performance sensitive, it tends to not matter at all. In the context of a proxy, things like that will add non-predictability. So that will end up adding greater variance to the greater variance to the latency of your requests. So without the runtime, that really is C and C++ before Rust. Well, I'm giving away the plot, but that's really C++. So you don't get any of these runtime features that come with Go and Java. So a lot more is left to the programmer to figure out how to run. So on the one hand, that means the programmer has to do a lot more work. So the programmer is spending a lot more time doing things that Go and Java do out of the box. So programmer speed, ergonomics is a big argument for using Go or Java, right? Or any runtime language. But the flip side is when the programmer is doing all these things by hand, there's a lot more ability to optimize and a lot more ability to structure things to guarantee predictable runtime performance. All right. So you might think that given some of this overhead that I have discussed with runtime languages, when implementing kind of infrastructure level projects, a lot C and C++ would be common choices. So this used to be true, like Apache, Nginx, MySQL, Postgres, a lot more mature, older projects. Those were written mostly in C. But for the past 10 years, I would say that hasn't been true anymore. So for example, a lot of databases tend to be written in Go or Java, so Cassandra, CockroachDB, etc. And there's like a number of newer infrastructure projects also just deciding to use these languages that come with the runtime. So like I said, no runtime, and that ends up meaning that as the programmer, you have to do everything yourself, especially memory management. That becomes the programmer's job. And while that allows the programmer to control, have fine-grained control and structure things for predictability, that also means that for C and C++, that there's no safety net that comes with the runtime. So the programmer is responsible for allocating, freeing, tracking pointers, making sure that you don't double free. So once you free a pointer, you don't free again. Bad things will happen. Especially make sure that once you free memory, you never use that pointer. You don't want any dangling pointers. When using arrays, you need to make sure that you never overflow those arrays, so you don't go past the bounds. You need to add bounds checking. You need to make sure that you initialize all your memory, especially because when you allocate memory in C++, that memory is uninitialized. It's like undefined what will be in that space. Best case scenario, it's random, but it can also be that old data is already stored there. And then especially if you start adding concurrency to your C or C++ projects, I would say have fun. That's extremely tricky to get right. When you get these things wrong, the program might access memory that it's not allowed to. So like maybe you have a dangling pointer, it points to some memory, that memory has been like freed, the operating system unmaps it, the memory to which this pointer is no longer valid, you try to access it accidentally, there's a seg fault. And debugging these in production, not fun. A great thing about Java and Go is that you never have to debug these things. it's not a great situation to be in. But it turns out that if you get a SegV, that's actually the best situation, because the worst situation is you end up with a whole number of the security vulnerabilities, and a large portion of security vulnerabilities and CVEs that come out for all of these various infrastructure level projects are due to bugs with managing memory. So when you make a mistake with managing memory and you have like a stray pointer or buffer overrun or something, that allows an attacker to access data that should not be visible to the outside world. So for example, you store your secrets in memory, and then you allow some vector by which an attacker can overflow a buffer and then read those secrets. Not good. Not good. Sometimes you might hear as a response to like, well, I don't want to write bugs in my code. Well, why don't you just use some linting tools? And it's true, there are linting tools for C or C++. So these are tools that just check your code and try to catch certain categories of bugs. And some of these tools are very good, but none of them are perfect. And I don't know about you, but I will just say I write bugs. It happens. I definitely write a good number of bugs, and I have written bugs that linting tools do not catch. These can translate to catastrophic security vulnerabilities. So I would say, while there are linting tools, the kind of historic choice has been this: speed on one hand, or safety. So safety, because you need a runtime historically to ensure that the category of bugs that end up being catastrophic from C or C++ cannot happen. So given this kind of trade-off, I would say it's very understandable why runtime languages end up being pretty popular for infrastructure level projects. Now, enter Rust, right? So it's a relatively new language. It's 1.0, I think, hit roughly 2 years ago, I think, right now. It came out of Mozilla Research. It bills itself as a systems programming language. So that systems programming language can mean different things to different people, but I think a fair definition is that you could write an operating system, you could write drivers, you could work with embedded systems using this language. So that roughly means that there is no runtime. And Mozilla initially started kind of this research project of trying to develop a new language because, as you are probably familiar, Mozilla writes a browser, Firefox, and writing a browser requires that you are very sensitive to security, because browsers tend to be attacked, like a victim of being attacked by hackers. Anyway, so security is very important, and speed is also important. Like, you want your browser to be fast. So historically, like other browsers, including Firefox, have avoided a number of potential speed improvements and optimizations, specifically around concurrency, because it's extremely difficult in C or C++ to ensure that, especially in the when adding concurrent logic, that you are not introducing security vulnerabilities. So Mozilla was like, okay, what if we can come up with a language that compiles down, it's a compiled language, like a language, and compiles down to an equivalent as C or C++. So at runtime, it would have the same characteristics as C++, but all of this while guaranteeing memory safety. So all the flaws around mismanaging memory, let's prevent those from happening. And the result of that is Rust. So going back to that kind of initial trade-off, there we go. It does this, it kind of puts in a wormhole, takes the two ends, and you end up getting both of them. So with Rust, you end up getting both the speed of C and C++ with the safety of a language with a runtime like Go or Java. And I think this is huge because, in part, it makes systems programming approachable to a lot more people. And for example, me, I come from a more dynamic language background. I wrote a lot of Ruby years ago, and I never really felt comfortable trying to do anything serious with C or C++ because I didn't trust myself. So Rust allowed me to get really much closer down to the metal while feeling comfortable. And I think a lot of people are in that boat, and it's a big deal, I think. So the way Rust gets you the best of both worlds is by performing all of its checks at compile time. If you write Rust and it compiles, you are guaranteed to not have written any memory management errors. So given that once it compiles down, there are no checks, there's no runtime, there's no garbage collection, there's no just memory management checks at runtime. I personally think, and it's a very strong statement, I think that no one should really start a new project with C or C++ anymore. So with some caveats, there are still some reasons, but for the most part, I think that is a true statement. And there we go. The way Rust is able to guarantee memory safety is thanks to a novel memory model called ownership. So it's a system that allows the compiler to ensure that values are only used once. So more specifically, that there's only one owner. So when you allocate some data, the compiler guarantees that there's only one kind of variable or struct field or one place that owns the data. So when that owner goes out of scope, because there's only one owner, the compiler knows that, okay, now we can free this data and this should never be used again. But of course, on top of that, you want to be able to use data from many parts of your code. So there's a reference system, kind of just like pointers in C or C++, or like object references in a garbage collection language. You can pass references or through functions or around your code, but the compiler ensures that when the owner of the data lives longer than these references. So that concept, it works with both stack and heap allocated data. So you get the same kind of flexibility that you would in C or C++, but without the hazards. I'm not going to go into a full Rust tutorial here, but I would hopefully convince some people that if you're not already familiar with it, to go and learn more after this. But now I'm going to kind of hand this off to Sean to talk a bit more about how Conduit uses Rust, and more specifically, like the libraries and whatnot, the ecosystem. So.
All right, let's swap around screens. Technology, yay. And we're good to go. All right. So Carl just spent some time explaining why we bothered to pick Rust. And then the next thing that we have to figure out when we're deciding to build a proxy in Rust is the ecosystem big enough, or does it support us writing the tool that we want to? So we decided we're going to build this thing in Rust. The first thing that we did was we hired a team of Rust people. So we have Carl, he's worked on Mio and Tokyo, and hired myself. I've worked on Hyper. Hired Brian Smith, he works in Ring. And I'll go into a bit more detail about what each of these are. But first thing was, many of these libraries already exist, and we brought these people in to try and work on something that uses all of these things together. So first thing I'll talk about is Mio. It's basically a cross-platform API for ePool, right? So it's kind of the foundation for non-blocking sockets, and it handles the C10K problem, which is basically you have a server and you want to handle a whole bunch of connections, over 10,000 connections at once. And the original idea is to spawn a thread for every connection. But threads get expensive, and at the same time, you're usually waiting in one of those threads for I/O to be available because the bytes have to go over the internet, across the ocean, or what have you. And so it becomes expensive in computer resources to handle a whole bunch of connections. So there's this thing, ePOL, and there's other systems. There's IOCP on Windows that allow you to listen to all of these sockets all on just one thread, right? So Mio is a library in Rust that kind of takes these different platform-specific ideas and rolls them into one. So you can listen to all these sockets on just one thread, and it's pretty cheap to do. So this already exists. It's getting pretty stable, and we're able to build off of this to get to the more interesting pieces. Another building block that has been seeing a lot of growth in the Rust community is futures. And you might have seen promises or futures in other languages. JavaScript has promises. Scala has futures. I think C# has futures and things like that. And they're really just a nice way to compose asynchronous code, right? You have something, it's basically a promise that sometime in the future, you'll get this value back. And you can combine together things like, after I get this, then do this other thing. And after I do this other thing, then do this next thing. And at the end, by the way, if there's an error, I need to handle this. But unique to Rust is that futures are actually a zero-cost abstraction. They're not this new heap allocated thing. Like in JavaScript, when you use a promise and you chain .then on everything, every single time that closure is being allocated into a new object on the heap, and it's slower for that. But in Rust, you just implement the future trait, which means that the future can just be a stack object and just be a state machine. So you could try and write a bunch of asynchronous code with Mio, and people do it with just some state machines, and you keep track of what state you're at, and you do something asynchronous and it's blocked. Well, okay, I'll wait some time and do a callback. But you can also use it with futures, and it comes down to about the same assembly at the end. So it's really a nicer way of writing asynchronous code without having to pay really any cost at all. And so then we can combine these two. That's what Tokyo is. It's an event loop, event-driven thing. Carl doesn't like that I use event loop, but it's, if you've used libuv or something, it's kind of like that, but it's in Rust. And it takes Mio and futures, reactor, and gives you sockets that you can read and write on. But the reads and writes give you back futures instead of having to do like a custom state machine and callbacks. The Tokyo is kind of a base library to do asynchronous network I/O. The other ones are below it, but hopefully you don't have to deal with them. And they allow us to use sockets and futures easily. So I've spent some time on Hyper, popular HTTP library in Rust. It's built on Tokyo, so you have the asynchronous stuff, you have the C10K problem solved for you. You don't have to build super complicated state machines, but instead you just chain together futures again. But this time you're using HTTP. And it's really fast, right? It's got client and server doing HTTP1. HTTP2 is coming soon. I'll talk about that in just a moment. And this building block is pretty important for us building a proxy that speaks HTTP. We have to talk to the control plane, and also when we receive requests, got to send out new ones. So we need both the client and the server to do this. But that's just what we started with. We wanted to build more because we needed to speak HTTP2. Hyperonly knew H1 at the time, and some other pieces as well. We built these things I'll talk about, H2, Tower, and Tower GRPC. So H2, the name of a crate, we just released a version of it last week. It's a client and server that speaks HTTP2. It's built on top of Tokyo. It completely implements the 7540 spec. So we have all of HTTP2 working. We pass H2 spec, which is a tool that you can set up to test your client or server, make sure that HTTP2 is working as the spec defines with shoulds and musts and so forth. Too far. And again, it's built in Rust, so it's fast, it's safe, and it's built on top of Tokyo with futures, and it lets us build a fast HTTP2 proxy, which Conduit needed. And then we got into this kind of less of protocols, and instead we worked on Tower, which is this framework of it defines a trait service, which is basically a fancy thing that's a function that, given a request, give me back a future response at some point. It's kind of inspired by Finagle or other RPC systems, is what they call themselves. So that's there. It is in quotes. And the idea is that they're composable. So you can compose various services together and chain them together, just like you can with futures. And of course, we have a bunch of other people here at Buoyant that have worked on Finagle. And so we were able to ask them a bunch of questions, what's the best way, lessons learned basically from having to work with a bunch of asynchronous code and Finagle's service and filters. And not only this, but then in order to use these various pieces in Conduit, we built a suite of middleware, a router, a balancer, you can do round robin or power of two, and buffer, to buffer requests up to some time, back off, retry, rate limit, and so forth. And these are, of course, at different stages of what we've needed, because, well, we needed some pieces more in Conduit and other pieces we didn't need. So that's how much we have at the moment. But of course, the idea is that this is abstract, agnostic to Conduit. So anyone could really use these things, just like Finagle is. You don't have to be writing a Twitter service to use Finagle. You can write anything. So you could, in your own software, be composing services. You need a router, of course. You want to balance things. So this is actually a fantastic place to contribute as maybe more strategies for how to balance things, or different ways of routing, different buffer systems, unbounded versus bounded, things like that. There's the Tower repo that's outside of Conduit to make it much easier to make contributions. And then after we had Tower, we worked on Tower GRPC. And the reason for this is actually because the controller has to talk to all the different data planes. And a very fast, efficient way of doing that is GRPC. Right, GRPC is this thing invented at Google. It's a language agnostic RPC implementation. So I was mentioning that Tower is like a RPC system. It's kind of just a framework for plugging in actual implementations. GRPC being one that tries to be really fast and efficient using protobuf, so that way things on the wire are serialized the best way possible. And it's very popular, generally used by a lot of large installations. Like I said, it fits into Tower's RPC framework system thingy. But specific to Tower gRPC is, first of all, gRPC can define these services, that say these are the different functions that can be called, and these are the types that you send to them, and these are the types that'll get sent back to you. And in Rust, well, Rust has a fantastic type system. So we thought we wanted to make it so you can use this great type system while using Tower and these gRPC services. So we built an extensive code generation system that's able to read a gRPC service definition file and output a bunch of a client and a server. So that way you can very, very naturally just talk to other servers in your network. And so, again, this is also a great place to be able to contribute back. If you use gRPC, then there's definitely things that we can add more on top of. More encoding. Some people use JSON instead of protobuf, and compression and things like that. But so we started with a bunch of things in Rust, but there were some things that didn't exist. And to build a proxy, we needed them. So we built them, right? H2, Tower, gRPC. And after having built them, we were able to ship Conduit 0.1. And, in the future, 1.0. All thanks to increasing the quality of the ecosystem. And thanks to that, the ecosystem benefits. Everyone else gets to have these extra pieces, all thanks to Buoyant sponsoring all this work in the Rust ecosystem. And so that's actually what I was going to talk about for the ecosystem. We've got some common questions here that we can talk about. And I'll start us off here. First question that we sometimes get: do I have to know Rust to use Conduit? I'll go ahead and answer this one and then see if one of the other presenters wants to answer the next. Do I have to know Rust to use Conduit? Absolutely not. Conduit is a program that you can install in your Kubernetes cluster, and just like every other piece of software, it runs without you necessarily having to know the things inside, how it's working. You just install it into your configuration, and while it happens to be using Go and Rust on the inside, if your service is all written in Java or Scala or Node.js or whatever, it doesn't matter, right? You don't need to know Rust to have used Conduit at all. Another question we get: will I have to make contributions in Rust? Carl, would you like to take a stab at this one?
Sure. Well, we would love to get contributions, but no. So basically, like I touched on before, the kind of brains of the service mesh is written in Go. That part is probably where most community contributions will be made, because that's where most of the service mesh logic kind of lives. So that's, Pick and Go was, for that component, was actually a big community contribution was actually a big factor there. Go is a more known language in kind of this community, so it made more sense there. So we hope, so first of all, obviously contributions are not required, but if you do, and we'd love to have some, odds are you'll make them in the Go side of things. The Rust side of things is mostly for the low-level bytes manipulation, but it's a good reason to learn Rust if you haven't yet. So we would also love to get contributions there.
Yeah, this is George. I think the only thing that I would add to that is that when it comes to contributions in community, I think with Conduit being such a new project, there are a couple of basic guidelines on getting involved and places to plug in. But I think in the next couple of months, what you'll see is that becoming a lot clearer, and having some set expectations around, how you work in Rust, or maybe onboarding specifically for Conduit. I think this webinar is a step in the right direction, but maybe formalizing that and socializing it with the community via GitHub, I think you'll see. And then as the control plane features of Conduit get a little fleshed out, as Carl's referring to, right, then I think those extensions will become more obvious as well, and we'll do some proper onboarding for the community in that respect also. So thanks, everyone. I think that answers some of the common questions that we also get. So we invite you to try Conduit for yourself. You can go to conduit.io, follow the Getting Started guide to try it safely on your Kubernetes cluster. And also check out the repo on GitHub, right? You can view source, and whether making contributions in Rust or in Go, we invite you to help us further develop the project or to use it, and let us know if there are issues or feature requests, right? Like any open source project. GitHub's a great place to interact with the project maintainers, or you can also chat with us via the LinkerD Slack group in the Conduit channel, or via our Discourse support forums. But before we get to questions, I'll give you a chance to submit any that are on your mind. We've got a couple of great questions so far. But in case we aren't able to fully answer anything that's on your mind, or if you're watching this recording and you have questions, I encourage you to reach out to us directly via Twitter, at Carl Lerche or at Sean Monstar. As you can see, both those handles are at the intro slide at the beginning of this recording. Or you can reach out to me directly, George Miranda, at gmiranda23, and we'd love to help answer anything that's on your mind. So with that, we get to the Q&A portion of today's webinar, and there are a couple of really great questions already submitted. So let's see. There's one question, actually, and this was on my mind as well when you were talking about promises and futures. How does Meltdown or Spectre, right? How does the Meltdown and Spectre vulnerability apply to Rust?
Yeah. So unfortunately, from what I know about those are not at all. Those are hardware level issues. So there are bugs at the chip level. One is Intel specific. The other is just general to strategies that CPUs use for optimization. So no, that is not something that Rust would protect against. But I think that's basically every single vulnerability that I kind of big one that I saw before that Rust would have protected against. So I guess it only protects the programmer against mistakes they can make and not the CPU choice they make.
Cool, thanks for that, Carl. Let's see, we have some more questions. Diego asks, is the plan to eventually replace LinkerD with Conduit when it catches up with the features? I think that's a great question. I will take that one. So right now, there is no plan to replace LinkerD, right? Conduit is a specifically different product with a different use case. I think, in the future, time will tell. Is this the right way to manage a service mesh, right? I think for a Kubernetes world, the Conduit approach is absolutely correct. There's a lot more in the world than just Kubernetes, right? Whether you're using DCOS, right? Gone down the path of Mesosphere, or gone down the path of Swarm or other container management platforms. I think there are solutions specifically for other approaches that LinkerD speaks really, really well to. I think what will happen in the next couple of months is that after Conduit becomes production ready, you'll see a lot of features that mirror some of the functionality in LinkerD, right? Some things around like retries, right? Resiliency, a lot more features around observability and a security and auth model. So I don't know. I think it's too soon to say, right? We'll see how Conduit does in the community. Again, I think they have wildly different use cases right now. Yeah, I think if at any point that was even an option on the table, there would have to be a clear migration path, and it would have to be clear what happens to LinkerD in that sort of world. But again, I think it's too early to tell. Let's see. There's a really good conversation going on in the chat channel, and I just want to capture this to make sure we don't lose it. The question is, does Rust come with any observability constructs? And to clarify observability, Prem, who's asking this, specifically referring to insights into memory and other resource usage.
Yeah. Okay, yeah, I can take it. So basically, since Rust compiles down to an equivalent of and target C, all the tooling that are available for observability with C level kind of programs can be used with Rust. So, and there are actually a lot of very solid tooling, like especially on Linux. I think Linux has some of the best, but I use Intel. I mean, I don't know if I use vTune a lot. Yeah, Intel. Anyway, but there's also like perf and lots of other nice tools on Linux. Yes, Valgrind is a really good one. But I will also say that Java has, and JVM has some really kind of top-notch observability tooling, in part because the runtime does allow to provide a bit more insight into what is happening at the code execution level, because the runtime knows a lot more about the code. There's also kind of a flip side in that you can implement a lot of observability features at the code level yourself with libraries, because the end targets result doesn't really come with the runtime overhead. So a lot of the visibility that the JVM does provide could arguably be re-implemented in library or C or C++. So I would say there's definitely a lot. And let's see, yes, also OS 10 does provide instruments, which is a pretty great tool. So there's a lot. Definitely the JVM provides also like some really amazing tools. I don't think it's just like different, I guess, like the different levels that you can get visibility into. So hopefully that answered the question.
Cool, thanks, Carl. There's a follow-up question from Prem, and I'm going to go ahead and take this, which is Istio versus Conduit ? I think we get this one a lot, and what I would say is there's a lot of activity in the service mesh ecosystem right now, and there are several other products, including Istio, including Envoy, right? Some other service mesh solutions. So I think that's a big question, and so I'm taking this one because I kind of want to plug our next webinar. In February, we'll be doing a webinar in tandem with folks representing the Istio project to talk about the differences between these products, between I guess philosophical differences, right, in design, the use cases where they shine, and we'll be exploring that question a lot more in depth because I think it's a very popular question. So I'm going to sort of delay that one for now because we could spend hours talking about it, and in February we'll spend at least 1 hour talking about that. So Prem, we'll definitely have some content for you in that regard. Let's see, we have another question. Fernando asks, other than languages and libraries, what are the main differences between the two implementations? I guess that means LinkerD and Conduit.
Yeah, I'm assuming that means LinkerD and Conduit. Well, one major difference is LinkerD is production ready, Conduit is not. But there are like the architecture kind of is significantly different. Like I said, like LinkerD runs is the assumption is that you run it in dedicated servers versus you can run LinkerD as a sidecar, but given that it was built on the JVM, it comes with that additional cost. And it's easier kind of to pay that cost with smaller number of large servers than a lot of small ones. There's a huge number of differences, I would say, between LinkerD and Conduit. So I'm trying to think like what are the high levels. I don't know if like Sean or George have more to add in that respect.
LinkerD is kind of a more general purpose. It works in a lot of different environments. Conduit is specifically designed for Kubernetes. Conduit can work, or sorry, not Kubernetes. LinkerD can work in without it. It can work with Istio and other environments. So and it's already in the JVM. So if you're already using the JVM, then the cost isn't as great as someone who wants to run a sidecar proxy like Conduit.
Yeah, and I think the only thing that I would add to that, aside from some of the performance costs and the resource costs, that mean there are different implementation models where each of them shines. I think the philosophy behind some of them is a little bit different, right? So as a preview to some of the things we're talking about next month, I think a good way to think about it is LinkerD lets you configure all sorts of things. It's a very powerful, very granular solution, but with that sort of power comes great responsibility, right? There's a kind of a steep learning curve and a cognitive cost to getting that granular with service-to-service communication. And while it's a powerful solution, right, there's some complexity there. There are a lot of moving parts. And I think Conduit, philosophically, very, very different, super lightweight. And when I say lightweight, not just resource consumption, right, but cognitively lightweight. Very few moving pieces, a lot less configuration, virtually no configuration required, just to get metrics and observability out of it, right? And I think there will be some configuration as we start to see constructs like, security and management policy that you can compose. But philosophically, I think Conduit is structured to be very, very simple and lightweight and not stand in your way, right? And so dedicated to Kubernetes, very simple and easy to get started with, versus LinkerD, multi-platform, super powerful, goes super deep, but also, comes at a little bit of a cost. So I think that's how I would sum it up. Let's see. I think we have time for one more question before we wrap it up for today. Let's see. We have a question. Isn't it really slow to develop in Rust versus easier to write languages? Actually, you know what? This also relates to another question. Let me see if we can lump these two together. Wouldn't using a mature language make more sense, as you wouldn't have to rewrite every single library, right? Which goes back to speed. Aren't brand new libraries less mature and more prone to having bugs? Great question.
Yeah, okay. So, there's a whole bunch of trade-offs, right, when trying to pick your language. So, yes, it's true. While it's true that Rust is much younger and the ecosystem is less mature, and that means theoretically, there could be more bugs with the implementations. The decisions that really factored into picking a language where it had to be close to the metal, predictable latency, fast, low overhead, lightweight. So given that was the hard requirement, we just couldn't use a runtime language. That just was ruled out. So the remaining decisions were C, C++, or Rust. Now, I would say that while it's possible there are more bugs, there might be more bugs in these newer Rust libraries, the severity of those bugs are going to be much, much lower. So security being kind of another paramount driver in this decision, we just did not want to pull in the risk of catastrophic security vulnerabilities, or at least we wanted to minimize that as much as possible. So the risk, the risk calculus there is that, yes, there could be less bugs quantity-wise in an established language environment like C or C++, but there are going to be security vulnerabilities. Just look at the CVEs; they don't stop, right? Go to curl, go to any of these libraries. The fact is, bugs are written, bugs exist, they are discovered. We just didn't want to pull in that risk as well. So I would say, given that using a newer language like Rust, while the libraries are less mature, the quantity and caliber and severity of the bugs that come with this newer language is greatly reduced. So given that trade-off, it seemed to us that Rust was the right choice.
Right. To add to this, basically there's going to be bugs in either, and so we can either choose to have bugs where things don't work, or we can have bugs where things work sort of, and then secrets are exposed or other really dangerous things can happen. So it's better to go with things break noticeably instead of things are leaked.
Cool. Thanks, Sean and Carl. With that, we are out of time for today's webinar. So thank you for attending. A recording of this session should be posted shortly. So if you missed anything, you should be able to find it in that recording. And if there's anything that we left unaddressed, which I think we got to all the questions, but I'll make sure that we did, I'll reach out to you for follow-up if we weren't able to get to it. We'll also be posting a follow-up to this session on the Buoyant blog. So if you have any questions as you watch this recording, please reach out to us directly, and we'll be happy to assist. So thanks, everyone. Have a great day.